Alright, so we're in the one categorical variable part 2 notes to kind of introduce the idea of hypothesis testing. First off, I'd like to say the good news, or possibly bad news, depending upon how you felt about the last set of notes, is that there's really no new math in this set of notes. We're going to be using the same type of math that we did in our previous set of notes, just formalizing things a little bit more. So that's why we're actually going to start with an example that could have just been in the last set of notes. So we're going to practice that, making sure we're feeling good about the math again, and then we'll talk about where that is going to leap to in this video today. So this could have been on your test, just like what you just took. To suppose we have a good example here where Chantix is an oral medication that's used to help people quit smoking, if you've never heard of it. They currently boast about a 30% success rate. So meaning that 30% of the people that use the medication will no longer be smoking after 9 months after starting their 12-week program. So we're just sort of using what we already know, right? So think about the idea here, the title of the notes, categorical variable. So we have the idea of, we have a smoker in front of us, they took the medication, the variable that we're recording is, are they smoke-free after 9 months? So the fact that it's a yes-no type answer is going to be a categorical variable that we're working with. This is our current rate that we're being kind of assuming that they're telling us. So we sort of have this idea that our P is going to be 0.3, so 30% of everyone who uses it should be smoke-free. So if we assume that this is true, what would be our sample distribution if we took a random sample of 140 Chantix users? So if we were to look at our formula sheets that you could have used during the test, so we're sort of with this idea of a sampling distribution. We're going to check our conditions, see if our conditions hold, and then if so, we know our sampling distribution. So we already know P, our P is our 0.3. The only other thing that we need to know is our N. And it told us that they're going to sample 140 Chantix users. So that's our N. So now it's going to go through first and check those conditions. So we still need to have our relatively random and unbiased sample. It says we're going to take a random sample of 140. Doesn't really give any other information here. So at least from what we know, there's no known bias. So we should be okay there. Our second condition is that N times P needs to be at least 10. So now we know N, we know our P, so we get 42, that's at least 10. And then we need to check to see that our N times 1 minus P is also at least 10. So now our 140. Doing our math here, we should get 98, which is also at least 10. Now again, using the ability to do the math, but what these numbers represent, so if 30% of all Chantix users are able to quit smoking, if we sampled 140, we expect 42 are going to be smoke-free. 9 months later, the other 98 will have gone back to smoking. So that's the idea of what those numbers are really checking. So since our conditions are met, we can now then use our sample distribution here, but we have to do that little calculation to find our standard deviation again. Alright, so P hat will be approximately distributed normal, centered at 0.3. Have to do our math here to find our standard deviation. And we should get 0.0387. That's what's going to go up here for our standard deviation. So that's our overall, this is our kind of big answer to the question, even though this stuff we had to check to make sure we could actually say this. Okay, so now we found in our sample that 25 were smoke-free after our 9-month period. So assuming our Chantix's claim is correct, what is our probability that we have 25 or less in our sample smoke-free after the 9-month period? Alright, so as usual, I'm going to start with my picture. Remember, I don't grade you on your ability to draw a curve, but hopefully the idea we still feel good about. I'm going to go out with my numbers here. Now, what number am I using? Right, I'm using the standard deviation at 0.0387. So we're going to subtract each time there, add each time there. I'll get all my numbers on here. So we have that. Now we have the idea of 25 were smoke-free. So the first thing I actually need to do is find my p-hat. So 25 out of how many? So out of our 140 that we sampled. So that gives us 0.1786. Right, on my picture, that's way over here. And then we went that or less. So we would shade to the left here of our little picture. So that's our goal, what we're trying to find here. Now thinking about sometimes this is why the picture can be helpful. Right, I have a very tiny part of this shaded, so I'm going to have a very small probability. We are 1, 2, 3, more than 3 standard deviations below where we expected to be. Right, so we're out of that 99.7% idea. So this is going to be a very small chance of happening. I already know that before I've even done any other math here. But again, as usual, our next step is actually find our z. That z is also on our formula sheet. So we have our p-hat now, we have p, we have n, so we have all the numbers to be able to do that. So we have our p-hat, we have our p, and from above up here, right, we have already the square root of p times 1 minus p over n is just at 0.0387. And doing our math, we get negative 3.14. Negative, since we're below the mean, more than 3 standard deviations below the mean. So again, that's what that idea is telling us here. We take that number to the table and get 0.0008. Now I assume at this point you can read the table. If you have questions on that, please make sure you're asking me. And then, so what's our actual answer? Well, that number, this 0.0008, tells us what's to the left of that number. We want what's to the left of that number. So that actually is our probability. Then the last thing we would do here is interpret that. We always start with that assuming idea, right? So we are assuming 30% of all Chantix users are successful at quitting smoking. And again, what we're saying with that is, well, that p is 0.3. The probability at 25 or less of 140 Chantix users being successful is our 0.0008. Or for percentages, that would be 0.08%. Nothing new, right? This is the exact same math that we did in the previous set of notes. So what's going to be different here is just what the title of the video is. So what does this actually mean? So right, you did all this work, you got this probability, and that's most of where we stopped in the previous sets of notes. But now, what does this actually mean? So let's think through this idea. So here's my question that we have. So based upon our love probability, do we think that Chantix is over-reporting their success rate after our 9-month period? Why or why not? Okay, so This is going to be a yes-no answer with a reason. So there's no more calculation being needed. We've already done all the math here that we need to do. Now what I like to have students do, so when I'm in a face-to-face class with this, I want you to think about what's your gut instinct. So are they over-reporting? Yes or no? What do you think? But then of course, not only have an answer, but have a reason what made you say that answer. Because what I'm going to do next is just point out a whole bunch of things that are going to support a certain answer, but sometimes we get it backwards in our heads. That's why I want to make sure you have an idea in your mind of what you think originally. So let's talk this through. Up here, we're assuming Chantix is correct. Right, 30% of all the users should be smoke-free after the 12-week program, 9 months later. So if we had 140 people, we would expect 42 of them to be smoke-free after 9 months. We had 25. Right, so 25 is obviously less than the 42. In fact, it's 17 less than the 42. Okay, is that a big enough difference to concern you? Okay, 30%. If we do that 25, that corresponds to a little bit shy of an 18% success rate. So, right, same idea here, that 18% is definitely less than what they told us. But we've talked quite a bit, like, right, if we have a 12% difference between two numbers, that may or may not be a big difference depending upon our sample size. Right, if I only place a sample a small amount, that is not that big of a difference, maybe. So that's where Z is so useful, right? Z measures how many standard deviations away I should expect to be. I expect to be right at 30, or pretty close around this 30 mark, right? So I expect to be pretty close to this number. The further I get away in either direction, the more I don't expect that to happen if they're telling me the truth. Right? We are way down here, right? We are more than 3 standard deviations below where we should be if they were telling us the truth. Right, now, hopefully most of us would agree if 0% of our people were smoke-free after the 9 months, we would definitely feel like something is up. Right, so the further below I get down here, the bigger concern I'm going to have. Is this far enough below to be concerning? All right, let's see if how I write my answer now makes sense. So I'm going to start with this big first word here. If. So this is a very important part. If. So if they are telling the truth, and by that I mean the 30% success rate, the probability or the chance of our sample happening or technically anything worse, we looked at anything below that as well, is what? So this 0.0008. Likely, unlikely to happen, right? That's very unlikely to happen. This is very unlikely. Okay, so what does that actually mean? As this is so unlikely to happen, if they are telling the truth, yet it did actually happen, I believe they are over-reporting. so here's the idea. Let's kind of talk about a couple of examples that aren't specifically here to see if that makes sense. Alright, so let's start with the first one. Right, you don't have your grades back on your test yet. But let's suppose, I told you, usually the average on the first test is about a 75%. Okay, right? You have no reason to not believe me if I first tell you that. But then you go and start talking to some of your friends, maybe you're in the class or took it last semester. The first person told you, I got a 60 on the first test. Would you still believe me? 75% average? That's just one person, right? They didn't do so great. That doesn't mean everybody didn't do so great. Alright, the next person you asked got a 70. Not too much lower, right? But, okay. But then if you find out, so we have a 60, we have a 70, we have a 45, we have a 38, we have a 29, a 71, 48. At some point, are you going to start questioning me? Okay, probably, right? Because if I'm telling you the truth, the chance that you run into everybody that did poorly and no one that did great on the test is so unlikely to happen. It makes you question if I'm telling you the truth anymore, right? Because it's contradictory to what I told you. So the same idea, right? So if we were to flip a coin, and a pretty big assumption we make about a coin, right, is that it's fair. If I flip it once, it's heads. Do you still think it's a fair coin? Okay. 2 times in a row, both heads. Still a fair coin? Now what if I flipped it 50 times and every single time it was a heads? Would you still think it was a fair coin? Probably not, right? And the reason because that is so unlikely to happen if it's a fair coin that you're no longer going to believe that it's a fair coin. So we have this idea, this assumption that we're making. We're getting our data and we're sort of seeing, okay, does it help confirm our claim or is it contradictory to what we believe? That's the idea of what we're doing in this set of notes, is talking about something we're assuming to be true, collecting some data, see if it's for or against what we said. Right? Does our data support it or is our data against it? That's going to be the goal in this set of notes.